That's better. Convolution, a term you've probably never heard of before, but probably used, whether it was probability or multiplying those tedious polynomials your teacher would give you in math class. They're used in pretty much everything from audio processing to image filters and more. But before we dive into these applications, I wanted to introduce it through probability. We all know the common example of rolling two dice and finding the sum of the two numbers. Usually we can represent this on a grid where each diagonal shows you the number of possible combinations that add up to a specific sum. For instance, if we wanted to know the probability of getting a 3, and assuming the dice are fair, so each probability is 1 over 6, we will get a total probability of 1 over 18. But can you think of another visualization to this problem? Well,
let's arrange our dice in rows, and rotate the second row and run it through the first. For each movement of our second row, we'll find that the overlap gives us the total of the two dice, and we can calculate the probability using this. If we continue doing so, we'll end up with exactly the same sequence as we had in our table. Just a different way of thinking about it.
so what if I told you to find the convolution of these two sequences? Well, if we use the same idea as before, we flip the second row and add the products of each two terms that overlap after each movement. Now we have our new sequence, which is a convolution of sequence A and B. But how could this be useful? Well, one example is the use of filters on audio, or the adding of reverb on an audio sample. Sound distorted is a sequence of data values on a computer. And let's say we have a digital sound file that we want to smooth out. Well, we can convolute this with a shorter sequence that is able to average out the values and give weight to certain values of our data. The result is a much smoother curve than we had before. Okay, cool, but what about image processing?
Well, if we want to blur an image, we apply basically the same concept, but in a two-dimensional sense. If you think about it, an image is just a sequence of pixels, and our smoothing sequence now is called a kernel. This can be of any size you'd like, but for the purposes of this explanation, it will be a 3x3 grid or matrix. I set it up so that the color of the middle value is given more weight than the values further away from it. So if we apply the same idea and move the kernel through each pixel in our image and find the percentage of each color we want to include, we'll end up with a new sequence of pixels that correspond to our new blurred image, which is the convolution of our old image and our kernel. This was Convolution in 2 minutes. I hope you liked it.